Now, by the way, just to remember, there's the derivative, there's the primitive. We're always starting from the middle. Okay, we're going to start from the middle and go outside from there. So let's start with our typical one, sine. Okay, sine. Now we know how to differentiate sine, right? The derivative of sine is cos, good. Okay, now let's just keep that there for a second. What about the derivative of cos? What's the derivative of cos? Minus sine, yeah, good. Okay, now, that's enough for me to now start thinking about, okay, well, what will the primitive of sine be, right? Because going from a function to its primitive, right, is the same as going from a derivative back to its original function. That's what primitive means, okay? So if I've got this relationship here, right, which ought to be the same as the relationship here, what would I expect to have come from if I end up at sine? And the answer is, okay, so it's got to be something to do with cos, right? But it's not just regular cos, because if I differentiate that, test it out, right, I won't land on sine, I'll land on negative sine, right? So that's why you have to put a minus there, and you'll get a double negative, and it'll cancel out, and that's why you end up with just regular old sine, okay? But, of course, you've got your constant flying around on the side, okay? All right, now, same point that I can make from here to here, right? That relationship ought to be the same as this relationship, yeah? So if I differentiated and I ended up with cos, I must have started from sine, right? With my constant flying in there, okay? Now, the next, I mean, your instinct for your next function will be tan, okay? Now, let's think about this for a second. We'll come back to him in a minute, but what will the derivative of tan be? Sec squared, right? Okay. So let's just note that, okay? Before I have a think about this guy, okay? That means that if I get sec squared, okay, and I ask you, well, where did this come from? If this is a function, what was its primitive? Well, you can see it's going to be the same relationship here. Right, so to go up one level, it's going to be tan x plus c. The derivative of sec squared isn't all that interesting because we don't really deal with it all that much. But from memory, I think it's 2 tan sec squared. But you can double check that with chain rule or quotient rule if you like. Okay. Anyway, now I want to come back to tan. Right now, it's interesting, right, because we don't have something which ends up, you differentiate it, and tan just comes out. Okay, at least out of this set, right? So, how can we work out what would its primitive be? I'm going to remind you that it's tan is really just shorthand for sine on cos. Okay. All right, so let's just think about that for a second. I'm going to leave that there, let it simmer, and I wonder if this will click for you. Okay. Well, it is a quotient, but it's not quotient rule. Remember, I'm ending up at this. I differentiate, and this is what I get. Not this is what I differentiate. Okay. So the bottom is have a think about it. Okay. Now, in order to try and get you there, let's have a think about not just trigonometric functions. You're going to wonder why I put this here, but what about log functions? Log x. What's the derivative of a log function? Just 1 over x. Okay, now that tells you that if you get 1 over x, right, I already know I can differentiate this. This is going to be that's x to the minus 1. So therefore its derivative ought to be minus 1 on x squared. And in the same way as I went from here to here, right, this is where I came from. This is log x plus c. Is that okay? All right, now, log functions on their own, they're pretty boring, right? We're used to stuff like this. Log of, say, I don't know, maybe, say, x squared plus 1. Okay? By the way, I'm deliberately leaving this part out because primitives of, I will come back to this one. We'll come back to him, okay? Primitives of log functions you really don't need to worry about, okay? What's the derivative of this? What rule am I using? I'm using chain rule, right? Because I've got a function of a function, right? So how does chain rule work specifically for logs?
You have the derivative of the little bit inside.
Yeah, that's right.
The bottom bit square.
that ring a bell?
Yeah.
Yeah. Now this is generally speaking, right? This is f dash on f. When I call that f, that's a bit nasty because I've got this already. Maybe I should call it something else. What shall I call it? G. G dash on G. Where that is G. Okay. Now I wonder for how many of you the cogs are turning. If I can say, look, if I differentiate this, I'm going to end here, right? Therefore, I ought to be able to say, hold on.
Nothing.
Don't be that guy in the movie theater who's like, oh, it's the bad guy, and everyone's like, ah, freak, ruin the movie for me, okay? Let everyone think about it, okay? Can you see how I've been going down this table, right? If I can say the derivative of this is this, therefore I can say the primitive of this is this. Right? Because I'm anti-differentiating. I'm just thinking, okay, where did this come from? Well, it's in this particular unusual format. G dash on G. G dash on G. Okay? So when you see a rational function like this, and they say, well, okay, what was its primitive? Where did it come from? Well, there's only one kind of function where you differentiate it, and you end up with f dash on f, g dash on g, whatever. Okay? It must have come from a log. Okay? All right, now let's climb back up the table. And you look at this. Now, it's not f dash on f, is it? Not quite, anyway. Because sine is not the derivative of cos, is it? That's pretty close, right? What is the derivative of cos? It's negative sine, right? So if I had this, okay, this is g dash on g, or f dash on f, whatever you want to call it, okay? So what do you think the primitive of this is? This is going to be a log of some kind, right? Log of, just log of cos x, yeah? And you think about how this would work. If I went back the other way, you differentiate, and you go, okay, it'll be f dash on f, g dash on g, it'll be minus sine on cos, it works. Okay? Yeah, thank you. Okay, so how am I going to fix it up if I don't have a minus sign there?
It's a minus sign in front of it.
Let's put one there. Okay, now if I'm going to put one there, you can't just multiply by numbers just because you want to, right? So I have to, whatever I do to this, there shouldn't be any net change, any total change. Okay, so there should be, if I want to.
Wait, no. Could you put the minus sign in?
Well, if I put a minus sign there, right, in order to make that the derivative of the denominator, right? In order to restore it and make sure I haven't thrown it off, I've got to put another minus sign way out the front. Okay? Does that make sense? Because now that is tan. The negatives cancel. This is still tan, even though it's a weird way to write it. Okay? So therefore, I ought to expect what's the antiderivative? What's the primitive of this thing? It's just this, right, with a minus sign out the front. Just in the same way as if I put a minus sign here, and put a minus sign there, right? Does that make sense? But I don't actually like that. Okay. All right, so now you can see, even though I was interested in trig functions, why I started looking at logs, okay? Because this particular trig function doesn't end up back at a trig function when you find its primitive. It actually ends up at a log function, which is somewhat weird. You got to be careful with it.
Doesn't that only work for?
Yeah. So there's issues of domain here, aren't there? Right? Because tan, except for its asymptotes, it just goes forever. Yeah, it exists for all root values except for those asymptotes. Whereas logs are not like that. You need to have positive values for cos. Okay. So therefore, and we're going to deal with the intricacies of this later. You have to be careful about the relationship between these two, but that's still the primitive function. Okay, it's still basically